In this recording, we are going to define what electrical flux is, and we are going to talk of Gauss's law for electrical fields. Now, what we define as flux, think of the word flux as coming from the word flow. Now, what we have to think of here, how much electrical field is going to flow through a particular area. The symbol we use for flux is this phi here, and the subscript E here is to tell us that it is an electrical flux. We will deal later on with magnetic flux. What we define as the electrical flux is as the magnitude of the electrical field times the area. Now, flux is going to have a direction as well, and we are going to talk about that in 1 second. Consider, for example, this area here in the form of tilted square, and try to think of the electrical field. Think of it as water. How much of the water is going to flow into that area? Of course, water that's coming at an angle to the area is not going to all go through that area. However, water that's going to come perpendicular to the area is going to flow through that area, and that's the idea. Okay, to illustrate that, we are going to use this simulation. So the area that we have here in a side view is going to look like just a line. And here we have the electrical field perpendicular to it. And then here is the front view. Now, the amount in this particular picture, since the area is perpendicular to the electrical field, all the electrical field is passing through, and we have a maximum magnetic flux of +1. Okay, let's go to the simulation and run it. Now, what if I change the orientation? Now, as I change the orientation, there is less of that area that's facing the electrical field, so I'm going to have less of a magnetic flux. In this case, it's about half as much, a little bit more than half as much, less than half as much. When the area is suddenly perpendicular to the electrical field, then I have no electrical flux at all. Now, what I'm going to do is rotate it in the opposite direction. Same thing. But now, what if I have it in the opposite direction? This is where direction is important. Now, what this is equivalent, is it going into that area or out of it? Think of it as a hose. Is it going towards the faucet or away from the faucet? That's going to matter. If it is away from the faucet, you are paying money for that water. If it is towards the faucet, which does not happen really in case of water, then you are not spending water. So in this case, but actually don't think of it as spending or not spending, but one of them is going to be a positive flux and the other one is a negative flux. So if the area, if the magnetic field, the electrical field is going in one direction, it's going to be a positive flux. If it is going the opposite direction, it's going to be a negative flux. So you can have negative fluxes. That's what's important. Here, for example, when it is totally opposite in direction to the electrical field, we have a flux of -1. Okay? That's the definition of electrical flux. So in other words, I wrote it as E times A, but it's really the perpendicular component of E, perpendicular to the area, times the area. And it's going to depend on the orientation to be either positive or or negative. If E perpendicular and A are in the same direction, then we are going to have a positive flux. If they are opposite directions, we are going to have a negative flux. Now, what's the use of token of electrical flux? It's this law here, what we call Gauss's law. There is ways to prove it. We are not going to get into that. But what Gauss's law says is the electrical flux through any closed surface is related to the net charge inside the surface by this expression, Q inside over epsilon 0. The flux is Q inside that surface over epsilon 0. We'll see examples to try to explain that. Where epsilon 0 is a constant, and it is actually related to that 9 10 to the 9 Newton meter squared per Coulomb squared. That's what that K is. E is, to say, electrostatic. So it is the amount of charge inside over epsilon 0. Okay, let's take this case, for example, here. What we have here is an insulator that is charged. What's going to matter in this case is what's the overall charge of that insulator. Then the electrical flux is just that charge over epsilon 0. And in this case, think of it as a sphere. The surface here is a sphere enclosing this other sphere inside. Now, the electrical field is perpendicular to the sphere throughout here. So in that case, this is just equal to E times the area of the sphere. And what's the area of a sphere? Okay, now just you need to remember a few things here. The area of a sphere is 4 pi, the radius of the sphere squared. So what this tells me, the electrical field is given by Q over 4 pi epsilon 0 r squared. Okay, now that's interesting. If you go back to this, that's where the 4 pi is. And actually this is going to give us the same expression that we used before for the electrical field. So the electrical field is not going to care if the charge is spread over an area this big or if it is all concentrated in the middle there. We are going to have the same electrical field that's given by that expression there. Okay. Now, this surface here that we calculated the area for is actually an imaginary surface, and we are calculating the flux over an imaginary surface that we kind of just draw to try to figure out the electrical field at that point, or the electrical flux at that point. Now, if we do our imaginary area inside the sphere, like in this case, now here we are not going to have the full charge of the sphere. We are going to have a portion of it. So in this case, the flux is going to be Q inside. So that portion of the charge inside over epsilon 0, not the full Q. The rest of the expression is the same. But in this case, what this is telling us, the electrical flux at that point is not going to care about these. And I can find the electrical field at that point without having to worry about that charge. These charges are going to cancel each other out. Their effect is going to cancel each other out, and they are not going to contribute to the electrical field. What if I have a hollow sphere? Okay, we have a sphere with a charge on it, and then this is our Gaussian surface, our imaginary surface. Notice there, since it's inside the sphere, there are no charges inside. so the flux through it should be 0. Now what about if it is here inside the actual conductor? It's the same case. All the charges are distributed around the end, so the flux through it is going to be 0. Now when it is outside, then that hollow sphere here is going to be considered like if all the charge is in the middle, and the flux, this is the first time we have a flux now, is going to be Q over epsilon 0. Now what about if I have a charge inside? In this case, I'm going to have an electrical field. What would the electrical field be? It's going to be Q over, I'm going to have an electrical flux, and that electrical flux is going to be Q over epsilon 0. Now, what if I go in the middle of the conductor? What would the flux be? Now, the idea here, the interesting thing is, because of this charge here, at this surface, at the inside surface, I'm going to have an accumulation of opposite charge. And in the outside surface, I'm going to have an accumulation of the same type of charge. So as a result, inside here, for that imaginary Gaussian surface, the overall amount of charge inside is just 0. It is the red charge here and the blue ones that are of the opposite sign and that are balancing out the red one. So overall, it does not matter how they are configured, but overall the amount of charge inside is 0. So the flux is 0. Now, in this case, this is where it gets interesting. So I have the red charge balanced by the charge inside, but then I have the charges in the outside that's left. So the overall flux is not 0 anymore. It's going to be Q over epsilon 0. And what's interesting, because of the balance, Q is going to be the same as the charge of the red charge here that we have in the middle.